So in this last video for symmetry and group theory, we're going to be looking at how to construct an MO diagram, so a molecular orbital diagram, for something other than a diatomic. And we will also be looking at how we can use symmetry and determine the chirality of a molecule and whether or not the molecule is polar. So I first want to start looking at how to construct a molecular orbital diagram. And the first step is to determine the point group of the molecule. Once you have the point group of the molecule, then you're going to determine the irreducible representations that describe the atoms in your molecules. So, for instance, if you have, say you had an ammonia, so the nitrogen would be a subset of the atoms in ammonia, and the hydrogens would form a subset. So you'd have to write reducible representations that describe the motions or the movements of those atoms. And once you determine the reducible representations, then you're going to find the irreducible representations that describe those orbitals. Once you have the irreducible representations, then you're going to look up the shapes of these salks, and these are in the back of your book. And the salks are just these symmetry adapted linear combinations. Then you're going to arrange in order of increasing energy the molecular orbitals. So lowest energy goes to the bottom, highest energy goes up at the top. But first you're going to determine what type of orbital it came from. So S, P, D, or F. So the S are typically lower, and then the P's, and then the D's, and then the F's. And then you're also going to analyze how many nodes, how many nodal planes do you have. The fewer the nodes, the lower the energy, because the more bonding the molecular orbital is. Then you're going to combine the salks with the same symmetry. So remember, the number of atomic orbitals have to equal the number of molecular orbitals that you create once you combine the atomic orbitals. Then you're going to estimate the relative energies based on the overlap. Finally, you want to do a computer calculation or experiment to help confirm your molecular orbital diagram. Because without experimentation, molecular orbital theory, really is meaningless. So you have to validate the calculations that you do. So since we used water as an example for looking at the molecular vibrations, we want to use water as an example for determining the molecular orbital diagram. So we said that water has C2V character. So we find the C2V character table in the back of the book. And we're going to start off by looking at the atomic orbitals for the oxygen. So the oxygen forms its own subset within the water molecule. Now the nice thing about the oxygen is that it's on the principal rotation axis. So it lies on the principal rotation axis. So that makes our assignment of the irreducible representations a little bit easier. So this is where we can also use this other information on the character table. So the PZ orbital, if I were to look at the PZ orbital and I do my E, so it stays the same. I do a C2, nothing happens. It stays the same, it gets a 1 as well. And if I do a mirror plane, so a reflection in the ZX axis, the orbital stays the same. And if I do one in the YZ axis, it also stays the same. So 1, 1, 1, 1 all the way across. And so you'll notice that this corresponds to the A1 irreducible representation. But the nice thing about this too is because that oxygen lies on the principal rotation axis, I could just look over here to the right here and I see the Z here. So this describes that PZ orbital. And I can do the same thing for the X, so the PX or the PY. But let's just go ahead and determine the irreducible representation for the PX orbital. So if I do the E, it stays the same, nothing happens, so you get a 1. For the C2, I rotate it about the Z axis. It changes direction, so the dark comes to the front, the light goes to the back, so it gets a -1 if I do a C2. If I do a mirror plane in the ZX axis, so in this plane right here, it cuts the p orbital in half, and the p orbital looks exactly the same, so it gets a 1. and if I do on the YZ axis, so it cuts it at the nodal plane here, so the dark will go to the light and the light will go to the dark. So it changes phases, so it would get a -1 in the YZ direction. So the px orbital is 1, -1, 1, -1. So this corresponds to the B1. So the 1, -1, 1, and -1 as well. And then the py, if I do the identity operation, it stays the same, so it gets a 1. If I do a C2, this flips sides, so the dark goes to the light, light goes to the dark, so it gets a -1. If I do a mirror plane, so if I reflect in the XZ axis, these phases change, they swap places, so they get a -1. And if I do one in the YZ axis, so in the plane of the computer board, it looks the same, so it gets a 1. And the PY has B2 symmetry, so the irreducible representation B2 will describe that PY atomic orbital. Now for the 2s on the oxygen, that has A1 symmetry, because if I were to do the irreducible representation for the oxygen 2s, I'd have a 1 for the EC2. The sphere looks the same no matter what. If I do a mirror plane in the ZX, it stays the same. If I do a mirror plane in the YZ, it still stays the same. So the 2s orbital has A1 symmetry. But now I want to move to the hydrogen atoms. And the hydrogen atoms, since they're connected by a symmetry operation, so let's say if I do a C2, this hydrogen moves to the other, this forms a subset. So all these hydrogens are related to each other by some symmetry operation. So now I'm going to write the reducible representation that describes my hydrogen atoms. So the 1s orbitals on the hydrogen atoms. So my reducible representation, if I do the identity operation, both hydrogen atoms stay the same, so +1 and +1. If I do a C2, they swap places, so they've moved. Both have moved, so they both get a 0, so we get a 0 for the C2. If I do a mirror plane, a reflection in the ZX axis, they swap places, so they both get 0s. But if I do a reflection in the YZ plane, they both stay the same, there's no changes in phase, so they both get a +1. So the sum of that is 2. So now I have to look to see which irreducible representations are contained within the reducible representation. And the nice part about this is a fairly simple reducible representation, because there's only 2 things that can add up to give you a 2, 0, 0, and a 2. And if I look at this, I only have +1 values in the A1 and the B2 columns. So I'm looking at this, so 1 and 1 is 2, 1 and -1 is 0, 1 and -1 is 0, 1 and 1 is 2. So I know that the irreducible representations that are contained with this are the B2 and the A1. So that was nice. I could do that by inspection. But if I couldn't do that by inspection, if I couldn't just easily look at it to see which ones are contained, I can still factor out. So I'm going to test out to see how many A1s are contained. So remember, I take 1 over the order, so 1 over 4, and then I take the reducible representation times the irreducible character of the class that I'm looking for, the A1 that I'm looking for, and the coefficient in front of the class of the 1. So the 0 times a 1 times a 1, the 0 times a 1 times a 1, and then the 2 times a 1 times a 1. So all that adds up to 1/4 times 2 plus 2, which equals 1. So there's 1 A1 within this reducible representation. So now that I know that I have an A1 and a B2 irreducible representation that describes the orbitals of the hydrogen 1s, So the calcs in the back of the book help you figure this out, but also the Mulliken symbols give you this information too. So remember, the A means that it's symmetric with respect to the principal rotation axis. So if I do a C2, both of those stay the same phase, so it has an A. And then if I do a mirror plane, it's symmetric with about to the mirror plane, so it gets a sub 1. But the B, if I do a rotation, it changes phases. And if I do a mirror plane, they also change phases, so it's a B2. But the calcs in the back of the book are labels of pictures of what these look like to help you make the assignments of the symmetry labels and what the orbitals look like. So now I'm going to start constructing my molecular orbital diagram, because basically what I'm going to do is I'm going to take the atomic orbitals for my oxygen and I'm going to combine them with the symmetry adapted linear combination of the hydrogen orbitals to create my water molecules. But because I've got the two hydrogen atomic orbitals, I'm going to combine them first to kind of create a mini MO diagram, and then I'm going to put that into my big MO diagram. So this is what I mean. Now remember, we've already determined the labels for our orbitals for the oxygen. We said that this 2s was an A1, and then the p orbitals on the 2p orbitals on the oxygen have A1 symmetry, B2, and B1 symmetry. So I'm just drawing a picture of those atomic orbitals, so the 2s, the pz, the 2py, and the 2px atomic orbitals on hydrogen. Now let's focus on the hydrogen orbitals. So we started off with 1s orbitals, one for each hydrogen. So I'm going to combine these to create kind of a mini molecular orbital diagram for these hydrogens. Well, there's two ways that I can combine them. I can combine them where they're totally bonding, so this is my A1, and I can combine them where they're anti-bonding, so this is my B2. So anti-bonding is higher than energy, so the B2, the anti-bonding, is higher in energy than the bonding, so we put it up higher. Now that I've got my combination of the hydrogen orbitals, now I'm ready to start building my molecular orbital diagram for the water. So the first thing I'm going to do is I'm going to look at which orbitals that I can combine. So I have to be able to combine things that are close to each other, things that have the same symmetry, so they're going to have the same symmetry labels, and of similar energy. So I'm going to start off with my A1. So anything that has A1 symmetry is of the right symmetry that it can combine. So I have one A1 on my hydrogens, and then I have an A1 here for my oxygen and another A1 for my oxygen. So this is my first A1, my second A1, and my third A1. And these were combined from these other three atomic orbitals. So those three atomic orbitals combine to make these three molecular orbitals. So a combination of the A1 from the hydrogen and the A1 from the 2s, this is a totally bonding situation. And then my next combination, so these are closer in energy, so going to have more character related to these that are combining to make this molecular orbital. So this is my 2A1. And then my last one is my 3A1. So this is the most anti-bonding in character, so this is the highest in energy. So I've created my A1s for my molecular orbitals. Now I can look at my other orbitals I have left. So I'm going to combine my B2s. I have one here for my in lower energy for my bonding, one up higher for my anti-bonding. So these are the ones that are coming together to make my molecular orbitals. So this would be the bonding situation where I combine the B2 from my hydrogens with the B2 from my 2p orbital on the oxygen. So we have this bonding overlap here. And then I could also combine these in an anti-bonding fashion. So notice that we have these opposite phases. So I have a nodal plane here and a nodal plane here. So the more nodal planes, the higher in energy, and the more anti-bonding in character it is. So I've combined my A1 and my B2s, but the only thing that I don't have left in my molecular orbital diagram is my B1. But my B1 doesn't have another B1 on the hydrogen side, so it doesn't have anything in the right symmetry to mix with. So I'm going to just move the B1 over at the same energy value, and this is going to be non-bonding because it doesn't have anything that it can mix with the right symmetry. So these are my molecular orbitals, and so you'll notice that the number of atomic orbitals equal the number of my molecular orbitals, so 1, 2, 3, 4, 5, 6 atomic orbitals to create 1, 2, 3, 4, 5, 6 molecular orbitals. So now I'm just putting in my electrons. I had 1, 2, 3, 4, 5, 6 valence electrons for my oxygen. I had 2 valence electrons for the 2 hydrogens. So that's a total of 8 electrons, and I just fill in my molecular orbital diagram using Hund's rule, the Aufbau principle, and the Pauli exclusion principle. So 1, 2, 3, 4, 5, 6, 7, 8. So this would be my molecular orbital diagram of water. Now we can also use symmetry to determine whether or not a molecule is polar. So if a molecule has an inversion center, belongs to a D group, or belongs to a cubic group, so that means either a tetrahedral or an octahedral group, or to the icosahedral group. So something that has a lot of symmetry, that molecule is going to be nonpolar. So a molecule cannot have an electric dipole moment perpendicular to any mirror plane, because a mirror plane would cause the vector of that dipole moment to be reflected on the other side, so those vectors would cancel each other out, so you don't have any net dipole. And a molecule cannot have an electric dipole moment perpendicular to any axis of rotation. Again, just to reemphasize, a molecule that is nonpolar either has an inversion center, belongs to a D group, is either tetrahedral, octahedral, or icosahedral. So if any one of those conditions are met, then the molecule is nonpolar. We can also use symmetry to determine whether or not a molecule is chiral. So if a molecule has an improper rotation axis, so remember that SN, then the molecule cannot be chiral. And remember, a chiral molecule is a molecule that cannot be superimposed on its mirror images. So remember, your hands are an example of chiral objects. Now, as you're looking to determine whether or not something's chiral or not, you need to remember the special cases of the S1 and the S2. So an S1 is equivalent to a mirror plane, and an S2 is equivalent to an inversion center. So if you find an inversion center or a mirror plane, then the molecule cannot be chiral. So in class we'll look at whether or not this molecule is chiral or not. And this is another example of what we'll do in class.